Elon Musk appeared at the 2026 Samsung International Smart Mobility Summit and shared his vision for a future filled with intelligent machines. He explained that Tesla's vehicles are essentially four-wheeled robots today, while the company is also working toward humanoid robots. Musk predicted that eventually there could be far more intelligent robots operating in the world than there are humans, and he believes this will most likely have a positive impact. A new video posted on X shows Tesla Optimus version 2.5 walking confidently inside Tesla's testing facility. The progress across the robot's different generations is genuinely remarkable. Compared with the slow and rigid movements seen back in 2023, Optimus can now walk with much greater smoothness, stability, and natural motion, coming surprisingly close to human-like movement. In less than 3 years, Tesla appears to have achieved progress that many experts expected could take a decade. And the most interesting part is that this is still only Optimus version 2.5. If the current version is already performing at this level, the obvious question is how much more capable the finalized Optimus Gen 3 could become. The latest technical information surrounding Tesla Optimus version 2.5 indicates that Tesla is no longer treating the robot as nothing more than a technology demonstration. Instead, the company appears to be optimizing it as a humanoid platform intended for eventual mass production. The improvements are not limited to artificial intelligence and software. Tesla has also made major mechanical changes deep within the robot's locomotion system, and those changes may explain why version 2.5 moves so differently from earlier versions. One of the most significant upgrades appears to be a much lower center of gravity. In previous versions, the battery and computing hardware were positioned higher inside the torso. This created an inverted pendulum effect, requiring the robot to use considerable energy simply to remain balanced while walking. With version 2.5, Tesla reportedly moved a substantial portion of the battery modules and power electronics lower into the pelvic region. This reduces upper body inertia and helps Optimus maintain a more stable walking speed of roughly 1.2 to 1.4 meters per second while potentially consuming up to 20% less energy than the previous Gen 2 platform. That improvement could become extremely important because energy efficiency will ultimately determine whether humanoid robots can function continuously in real manufacturing environments. Another development that has attracted attention is Tesla's apparent use of a 4-bar linkage mechanism in the joints. This type of system is commonly associated with advanced biomechanical and prosthetic applications. The mechanism can allow the knee to reproduce more natural human-like movement patterns without requiring an excessive number of complicated actuators. Instead of producing the stiff, segmented movement common in many humanoid robots, the 4-bar linkage can distribute force and torque more naturally throughout the walking cycle. This could help explain why Optimus version 2.5 now appears considerably smoother, particularly during the transition from heel contact to toe lift while walking continuously. Tesla also appears to be moving away from conventional position-based control toward a high-frequency torque control architecture. The internal feedback system is reportedly capable of operating at frequencies approaching 1000 Hz, allowing the robot to measure and adjust joint forces almost every millisecond. Force sensors positioned around the ankles and knees can continuously monitor ground reaction forces whenever the feet contact the surface. This enables Optimus to adjust its movement in real time rather than simply following predetermined steps like earlier generations. That represents a major improvement, because even very small mistakes in force distribution can quickly destabilize a humanoid robot. Another subtle but important change can be seen in the movement of the pelvis. Optimus now appears to use natural lateral tilting and rotational motion of approximately 3 to 5 degrees during each step, much more closely resembling human biomechanics. As a result, upper body movement has reportedly been reduced to less than 1.5 centimeters. This can help the camera system mounted on the robots head maintain more stable visual information for Tesla's AI vision networks. That is particularly important because Tesla appears likely to apply a vision-based AI philosophy similar to the one used in its autonomous vehicles. Instead of simply following rigid pre-programmed paths, the robot can continuously observe its environment, interpret what it sees, and react accordingly. The bigger question is how Optimus handles its surroundings while moving through complicated factory environments. Rather than depending entirely on pre-mapped navigation, the robot is believed to continuously construct a live three-dimensional representation of the environment through multiple neural network vision systems. Cameras positioned around the head can analyze depth, object boundaries, floor geometry, and movement trajectories at the same time. This allows Optimus to anticipate obstacles before physical contact occurs instead of reacting only after an impact or loss of balance. In practical terms, the robot is starting to behave less like a machine simply following commands and more like a system continuously interpreting the world around it. This environmental awareness becomes especially important inside factories, where workers, carts, machinery, components, and other objects are constantly moving. Earlier humanoid robots frequently struggled because they depended heavily on scripted movements or expensive external sensing technologies such as LiDAR. Tesla appears to be pursuing a different strategy by relying primarily on AI vision and real-time inference. Using an architecture similar to its autonomous driving systems, Optimus could eventually identify narrow pathways, recognize moving obstacles, determine safe locations for foot placement, and adjust its balance dynamically before instability occurs. If this approach works as intended, it could represent one of the most significant transitions in humanoid robotics, moving from rigid pre-programmed automation toward adaptive autonomous movement. Tesla has also redesigned the way Optimus uses its arms during walking. On older prototypes, the arms often remained relatively rigid or reacted only when the robot needed to recover its balance. On version 2.5, the arms appear to swing naturally out of phase with the legs, similar to a human walking pattern. This movement helps counteract rotational forces generated during locomotion. The result could allow the robot to perform sharp 90-degree turns and navigate narrow factory pathways as tight as roughly 80 centimeters without stopping to rebalance. Most importantly, these upgrades are not simply intended to create impressive footage for social media. Tesla appears to be trying to demonstrate that humanoid robots can achieve natural movement by combining AI-based control with mechanically efficient designs rather than depending on extremely expensive and overly complicated actuator systems. If Optimus version 2.5 can already achieve this level of dynamic balance, environmental awareness, and fluid movement before Gen 3 arrives, Tesla could be getting much closer to deploying thousands of autonomous humanoid robots inside real-world manufacturing facilities. Now look at the pilot production line revealed by Sawyer Merritt on X on May 21, 2026. This footage represents more than a look inside a clean factory. It points toward a major transition in Tesla's humanoid robot program, moving from research and development toward a large-scale, highly modular, software-driven manufacturing operation. For years, many people viewed the humanoid robot race primarily as a software challenge involving experimental hardware. The newly revealed pilot production line challenges that assumption. It suggests that one of the major challenges of the humanoid era may not simply be artificial intelligence, but the ability to manufacture these extremely complicated machines at massive scale. One of the most interesting details in the footage is Tesla's aggressive reuse of existing factory infrastructure. Look closely at the text shown in the lower left portion of the footage. Model S and Model X production lines will produce Optimus. This represents a significant operational change. Earlier in 2026, Tesla reportedly ended production of its legacy Model S and Model X vehicles at the Fremont factory and began dismantling those assembly operations. Rather than spending billions on a completely new manufacturing site and waiting years for construction to finish, Tesla appears to be repurposing the existing premium factory footprint for an Optimus Gen 3 pilot production line. The move is supported by a major 2026 investment program, reportedly exceeding $20 billion. By reusing existing infrastructure, Tesla can potentially avoid years of construction delays. This pilot facility can serve as a critical testing ground for large-scale manufacturing. While the initial line is intended to identify and correct early assembly problems, it can also function as a blueprint for a much larger factory conversion. The planned expansion is expected to reach completion around late July or August 2026. At that point, the site could potentially provide an initial annual production capacity approaching 1 million units and serve as a model for the future hyperscale facility at Gigafactory Texas. But how does this factory actually operate? Tesla appears to have moved away from the conventional continuous automotive assembly line concept. A humanoid robot is an extremely dense electromechanical system containing thousands of unique components, numerous precision actuators, tightly wound copper stators, and miniature sensor systems. In a traditional linear assembly line, even a small tolerance problem, or something as simple as a cross-threaded bolt at one station, could create a major failure and potentially stop the entire production process. As Elon Musk has previously explained, production ramp-up can be difficult to predict because the slowest or least efficient element in a production system can hold back everything else. Tesla's solution appears to be a highly advanced digital cellular manufacturing layout. The factory floor is arranged into two symmetrical rows containing independent, self-contained work cells supported by large black steel gantries. Each cell functions as its own localized manufacturing unit. Industrial robotic arms and human technicians can assemble specific modules, such as the advanced 22° of freedom dexterous hand, lower limb actuator assemblies, or the central chassis containing the AI-5 inference processor and battery system. The green status lights visible above the gantry structures indicate that the individual cells have reached synchronized operating cycles. If accurate, this would suggest Tesla has made significant progress in reducing early production variability. Individual modules can be assembled according to standardized procedures, allowing production to continue without many of the bottlenecks normally associated with pilot manufacturing. The wide and uncluttered central pathways between the production cells are also important. There are no obvious permanent overhead rails, underfloor chains, or fixed barriers restricting movement. Instead, the layout appears designed for flexible transportation using automated guided vehicles and autonomous mobile robots. Large overhead cranes from industrial equipment manufacturer Airbus handle heavier logistics from above, leaving the factory floor open for autonomous vehicles to move components between different manufacturing zones. This creates a manufacturing environment that is heavily controlled by software. That flexibility is particularly valuable because Optimus hardware is still evolving rapidly. Permanently fixing physical infrastructure into the factory floor could become a major limitation. If Tesla engineers change a joint sensor architecture or modify a thermal management component next month, they would not necessarily need to rebuild the entire production line. Instead, the software can potentially be updated so autonomous mobile robots are redirected toward newly configured assembly or testing stations. That level of flexibility is exactly what Tesla would need to pursue aggressive short-term production goals while maintaining the ability to scale over the long term. For the remainder of 2026, the pilot line and later Fremont expansion are expected to potentially produce between 50,000 and 100,000 fully operational Optimus robots. These initial machines may not be intended for consumers. Instead, they could be deployed directly into Tesla's own vehicle and battery manufacturing operations, as well as the Tesla Cortex-2 AI data center. Looking further ahead toward 2030, Tesla has discussed an ambitious vision involving millions of Optimus robots, with a potential target retail price around $30,000 per unit. By deploying early production robots into its own factories, Tesla could create a closed-loop feedback system. The robots would gather operational data, improve their AI systems, and potentially contribute to manufacturing components for future robots. This creates a cycle where artificial intelligence and physical production can improve together while manufacturing costs gradually decline. Tesla is effectively attempting to build more than an advanced humanoid machine. The company is trying to develop the entire industrial system required to manufacture artificial labor at a scale that could be unprecedented. The potential economic impact would be enormous. The real question is whether competitors that are still assembling humanoid prototypes manually inside isolated research laboratories can match the development speed, manufacturing flexibility, and potential economics of Tesla's modular, software-driven factory approach. Thanks for watching. Make sure to hit the like button, subscribe to the channel, and turn on notifications so you don't miss our next breakdown. See you in the next video.